So in this handout, we will be looking at operations we can do on pixels, okay? And especially, well, there will be color operations. So color is a very important aspect of pictures, and it conveys a lot of emotion. And when you work in movie, so actually I worked in movie post-production for a while, the color, the color grading of your movie is super important, okay? And it's something you really spend, you have, very skilled artists trying to change, do the right touch to your picture, okay? And usually the type of operations you do actually quite simple, okay? So I just listed between these two slides, three types of operations you will have, actually two maybe here. So the first one is, what you apply is very simple, it's just a linear transformation of your color. So here I write the expression. Imagine that they are vector expressions, okay? So, well, it's an expression you apply for every single channel. So let's say you have the red component of your pixel where you can apply, A times the red plus B, okay? So A and B are the gain and offset of your linear transformation, and you apply that for all the pixels in your picture, or at least in parts of your picture. So that is actually tantamount to altering the brightness and contrast of your picture, and I will show you examples of that. So, I mean, if you change the B, basically you change the brightness of your picture. So if you look in Photoshop, if you play with Photoshop, if you want to change the brightness, that's your B, and if you want to change the contrast, that's your A. So if you increase A, you increase the contrast. If you decrease A, all the colors will be kind of similar, and therefore you decrease the contrast. Another operation that is quite common is a gamma type operation, and basically you take a power of your color, okay? And that is something that happens quite a lot. It's a correction you had on your CRT screens and so on, or if you go from a Mac to a PC, for instance, this is kind of a transformation that would change, okay? So people usually went for 2.2 gamma or 1.8, and that comes from the fact that that comes from Weber's law, okay? So we perceive changes in color differently as the intensity of it increase, right? And so a way that to better represent picture that takes less space is to compress that space using this gamma transformation. So you're more sensitive to the changes in the low levels, in the darks, than you are in the brights. So you can compress the brights a bit more, have the steps a bit bigger than you have in the darks. We'll come back to that at some point. So let's see the effect of the color transformation on histograms. Okay, in the next few minutes, I just want to focus on the relationship between histograms and pictures, and because I feel like it's a very useful thing. I mean, histograms are kind of the primary source for you to, pretty tool to look at pictures and to see what's going on. So on the left you have the original picture, on the right you have the histogram for that picture. So histogram means, okay, everybody should know, but basically on the x-axis here you have the intensity of your pixel, okay, so going from 0 to 255. And on the y-axis you have the frequency of that particular color or intensity in the picture, all right? And so either you record that as so frequency means it's a ratio, or you can, histogram usually just count the number of pixels that have this particular value. And what you see here is a very typical histogram of natural images. The histogram is relatively smooth and spreads over all the color, and you can see here there's kind of a peak here around 200. Can you tell me what this peak corresponds to?
Sky at the beach.
All right, sky at the beach. All the bright pixels, and usually, so usually when you have a peak in a histogram, that corresponds to the biggest region of, homogeneous region of your histogram. Okay. If you have a lot of textured area, usually textured area will be spread, could be quite spread out. Okay, I mean, and that makes sense because if you have something textured, the values change quite a lot. Okay, so if you see its texture, it means that you see brights and darks and mid-tones and so on, and therefore you see a bit of all the pixels, and therefore there is no one range of intensity which is prominent. Okay, but here you have clouds, and the clouds, they're all kind of just very bright. So therefore you have loads of very bright colors. All right, so it's just kind of an interesting point here. Is like usually reading histograms, you can relate to them and say, if you have a peak like that, probably means like there's an object which is very big, and in natural images, there would be the sky, for instance. Right, so if you apply this linear transformation, so we reduce the gain to 0.5, but we add an offset. This is what you obtain. So the result is like the colors are more subdued, and you know, it's less contrasty. Okay, so you reduce the gain, and there is less contrast, and you can see the contrast in the histogram. What is happening with the contrast? Okay, so basically now, if you flip back, the histogram is all squashed. Okay, so here all the colors, like the intensity, was spread for the whole range of possible values from not quite 0. So if you look here, it starts at 20, 25, and you know, ends at 250. I kind of use it the entire range of possible brightness from very dark to very bright. Okay. By doing this, we reduce that range. Okay. So now the darker set at 76, which makes sense. We have an offset here, but it ends much shorter as well at 200, and that comes from the fact that you actually only took half of the value. So this 0.5 actually means that we have the range of values we are going to use, and therefore it's going to seem very gray and just monotone. Okay. You can see as well, like the shape is roughly the same, but you have a number of little artifacts and little things going on. I will just come into more details of what is going on here. Similar effect here, not quite similar. So here we're applying a gamma transformation. So we apply power square root, okay, and similar. Okay, so you see the effect on the picture here. Feels brighter, and you can see it's been more squashed towards the right side of the histogram. So it means that the colors are more brighter, but as well the range has been a bit compressed somehow. And inversely, if you have a high gamma, so 2.2, then you have something a bit more contrasty. Okay, so you have much better range. But, and you see that a lot of colors are becoming very dark. Okay, you can see that in histogram, and that is because when you apply something to the power of 2.2, then because all the values here are between 0 and 1, in that transformation. I should have said that before. When I apply the gamma, I assume that the value is here in floating point between 0 and 1. Okay. So when you do that, then a value of 0.1 will be to the power of 2, so squared almost, so it means like it's even smaller. All right. So we're trying to see the next 10 minutes, so to see what the exact operation applied to histograms in color. So in the following, we assume that you have a transformation from 0255 to 0255 that will map just in intensity, so forget about color, from U, so our color, to T of U, okay? And basically this is what's happening, okay? So your histogram, so I just wrote here the formula for computing directly the histogram of the transform image. So try to forget about the picture. I'm just looking at apply this transformation, color transformation. I already have one histogram. I want to predict what the next histogram should be without having to recompute the picture, okay? So I have my picture, typical scenario, okay? I have the picture, I want to apply a color transform, and that has an effect on this histogram. Now here, what I want to do is kind of bypass the whole picture domain and just say, I have my histogram, I have my color transformation, can I compute directly what the histogram will look like after transformation? So this is what's happening. So if we have a color V, and we're looking at estimating what the histogram, the frequency of that particular color will be in the transform image, so that's the left-hand side here, I say that it's a list of all the colors U that will be transformed into V. Okay, so I try to find the inverse of V. Okay, so I'm looking at trying to find what the frequency of V. Well, to find what the frequency of V, I need to try to find all the color U's, the original color, that will be mapped into that particular color V. Okay, well, that's what it is here. And that means that when you're working with, because most of the time you're working with integers, okay, there's a lot of colors that won't get matched to something. So if you look here, coming back to that particular example here, you see there's these gaps, some of the values actually in the histogram are set to 0. And that is because some of the, you transform these discrete values from 0 to 55, and you apply this transformation, and what will happen is like some of the values will map to the same value, and some of the, sometimes you will have values that are never mapped to anything. So you don't have any pre-image on it, okay? So if you look carefully at this value here from your histogram, so that's a zoom, okay, on the mapped histogram. So if you look at the value 110, it turns out that there is no value in our range that we had in the existing picture that mapped to 110 after color transformation, right? So therefore, don't count any pixels in your transform image. You don't have any pixels that have 110, and therefore the histogram is 0, okay? Conversely, you'll have sometimes, and that is the case here, you would have some pixels, you have the spikes here, so you have some pixels where two values have mapped to the same value, and therefore you have a bigger spike there, all right? So it's a bit of a mess, right? So some values, merged, and some values kind of disappear. And therefore, this is why you have this kind of a bit of noisy representation of your histogram. So we started from a smooth histogram, but now it's a bit messy because there's a lot of values for which we actually don't have any more representation. Right, so I want to finish on that by talking about histogram equalization, how you can increase the contrast and trying to make the picture more interesting for analysis, especially if you're working, say, with medical imaging, okay? So we're going to look at a particular class of color transformation, which are monotonic increasing. And now, so monotonic increasing just means that if you have one intensity, so U1 that is smaller than another one, so you have U1 less than U2, then after transformation, you still have the same properties. So the mapped color T of U1 is smaller than T of U2. And now this seems a bit arbitrary, but actually that covers pretty much all the cases we have, and definitely that covers what we've just shown before. So all these cases are definitely like this. So if I is say 0 or I is 1, so that's two different values, then you have, the G would be transformed to 0.5 plus 76 or 0.5, well, anyway, you can do the maths, that'll just be fine, okay? So if you have two colors, like two I's, that are one less than the other one, after transformation, there's still, the order will still be preserved into which one is the darkest and which one the brightest. So we're going to look at this case, and what you realize is, you say, okay, if I have a particular, if I start to, in the histogram, we'll be looking at pictures that have all the pixels that have a particular color, and in this case, we're going to look at something slightly different. We're going to look at the threshold. We're trying to find all the pixels that are less than a particular value. And so we're going to look at all the I of x that are less than this particular threshold in intensity u. And then what we find is that the threshold, if you just keep that threshold, the threshold will still be the same, the picture will still be the same, as in like the pixels that are less than u in the picture before color transformation would still be the same as all the pixels that are less than this time t of u, the transformed version of that threshold. Okay? And that's what we have here. So in a way, another way of expressing that is to say the probability that your pixel, for a pixel to be less than a particular intensity, the same as the probability for the transform image of a pixel to be less than the transform value. And so let's see an example of what I'm talking about here. So that's your original histogram, and you're looking at the value I of x for 150, and you're going to transform that that histogram using a gamma correction of 2.2, and that's going to stretch your histogram here. Okay, and the transform value for I of x by that transformation will give you 79 here as a value. Okay. So move from here to here. Okay. Now we recognize the problem of the values being set to 0, but the shape otherwise is kind of similar, just a bit squashed, I suppose. What you see here on the bottom is the cumulative function of this histogram. So basically, what you have here is, if I look at 150, is the cumulative probabilities of being each of these particular values. And that gives us a number, so 0.3. So 0.3 here is the sum of all the percentages. Well, 0.3 would be 30%, okay? So 30% here is the sum of all the percentages under the curve here. And that tells us that if you take a pixel at random, you have a 30% chance that the pixel would be less than 150. Okay, so that's what this curve does. So obviously, if you have a pixel that is 255, then you have 100% chance that all the other pixels are less than 255. Okay, so that's your probability distribution. And what is interesting is that to find where to go, okay, in the next frame, the next after correction, is that the probabilities that you have here stay the same. So after applying your color transformation, the probabilities stay the same. So if you look at the equivalent of 150, so that's 79 in this one, then the probability in the new picture that a pixel is less than 79 is still 30%. Okay, because you haven't changed the order. The order is still the same. Okay, so when you apply 99% of all kinds of color transformation, usually the relationship, the order in which the intensities are laid out, is still remains intact. Okay. So all that is a bit subtle, right? But what that means is that you can do color equalization, okay? And the way we're going to do that is by saying that we are going to try to do the reverse, okay? So we know how we have a color histogram, and we know when you apply a function what the effect on this color histogram is. And we kind of have a nice little diagram here to correct that to the cumulative histogram. Now, if you apply, try to find that exactly. Right. I don't have a good diagram here. Sorry about that. So if you try to, so in in histogram equalization, so I'll just show you, one example of what color histogramization is. Something like that, okay? So you start from this picture where you have your histogram on top here, and you have your cumulative histogram here. And what you want to do is to apply some kind of color transformation, okay? That will be such that your the result of your histogram is kind of a flat histogram. So it means like you're trying to maximize the whole range of your contrast by making sure that every single color is used as much as another one, okay? So what we're trying to do is to say, I know that when the histogram is very spread, it looks very contrasty. So what kind of picture can be the most contrasty possible, okay? Well, that would be a picture who has a histogram which is as flat as possible. Does it make sense? All right, so remember the relationship between the histogram and the colors. So your colors, something contrasty means like you have some very dark and some very bright colors, okay? And if you push the reasoning to the extreme, you say, I want the picture to be as contrasty as possible. That means like you want to use all the possible colors in all possible ways, so your senses are being blown away by all these variations in the contrast, okay, in the histogram. So histogram equalization, the idea is like, can we find a transformation that will transform this original picture we had here into a picture whose histogram is roughly flat. Now you can't have something totally flat because some of the values that we talked about like has to be set to 0 and some of them won't be set to 0 and so on. But that is pretty much flat. So thinking in reverse, okay, if you have a flat histogram, if you look at what the cumulative distribution function for that histogram is, that'd be a straight line, okay? So what you say is, if you look at, say, intensity 255, okay, so you have 100% chance that all the pixels, are less than 255. But if you take a pixel of 150 or 125, something like that, then you have a 50% chance that the pixels are either darker or brighter and so on. So you have a nice way of defining what this cumulative histogram function should look like, and should just basically look like a straight line. So coming back on that means here that we can find a way of defining that function. And basically, the way you do it is by you say, I have this input histogram. I know that is my cumulative distribution function. And now, my target function should be actually not this function here, but a straight line, a straight ramp, okay, going from 0 to 1. And that straight ramp will be the target for my cumulative histogram. And basically, the way you're going to proceed to find what is the color mapping you need to have, so you're going to start here. You say, I want a value of, so my value of is 150. I want to know what the transform value for 150. I say, first compute what the cumulative histogram is, and give me the number of pixels that are darker than this value. And I say I have 30% of the pixels that are darker than this particular value. Then I will look back here and look at for what value I have 30% of the pixels that are darker than this value. Okay? And I will look back and say, okay, well, in that case of gamma 2.2, I had, the value was 79. In the case of cumulative histogram that is coming from a histogram equalization, there'll be a different value. But basically, you record that value and you say, well, that value is exactly the value I should map to. Okay? So you do basically the analogy in the space of the cumulative histogram. So you look at the real way of thinking about that, look at the percentage of pixels that are darker than you. And that number shouldn't change, regardless of the color transformation you do. All right. That's how you should think about that. That's a key to understand that. And that gives you a nice mechanism to do it. So here, you apply that mechanism, you go from the original picture, and by looking at the cumulative histogram, you can transform that find a transformation that will transform that particular histogram, cumulative histogram, into that particular ramp, and that transformation will allow you to obtain this version of it. And indeed, as you can see, this is quite used in scans and so on, X-rays. So on the left is the real picture, and all the levels, like the very low contrast. That means your histogram is all compact. You don't see much detail. But if you use the entire range available to you, then you can start to see more. Okay, and the takeaway from that, I suppose, is this relationship between histogram and the visibility of what you do. Okay, so if you stretch your histogram, if you use all possible colors as much, like you balance it out, then you have something which is more visible to you and be giving you more contrast. All right, I'll leave that to here, and we'll finish that next week.